Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about torque. Our objectives include calculating the torque on a rigid object and applying conditions of equilibrium to analyze a rigid object under the influence of a variety of forces. So let's start off by defining torque. Torque, which gets the symbol, the Greek letter tau, is a force that causes an object to turn, and it's a vector. Torque must be perpendicular to the displacement in order to cause a rotation. And the further away the force is applied from the point of rotation, the more leverage you obtain, so this distance is known as the lever arm, R. So if we look here, for example, on a wrench, using that to turn this piece over here, we're applying a force at some angle, theta, with what we call the line of action. The distance from the center of our rotation to where we're applying the force is our lever arm, R. And the only force that's really going to matter here is this piece of the force, the one that's perpendicular to the line of action. So that's going to be F sine theta. If we draw it over here, it may be a little easier to see. F sine theta at some distance r when we're trying to find our torque. And you probably know by experience, if you try and apply a lot of force here, not going to do a whole lot. Apply that same force further away, you get more rotation. That's because you have more torque. So torque is the r vector, the distance from that point to where you're applying the force, that vector, crossed with your force vector. And if you remember our cross products, if we want the magnitude of the torque, that's going to be Rf sine theta. Now the direction of the torque vector, again, is a little bit counterintuitive. It's perpendicular to both the position vector r and the force vector F. So you find the direction using the right-hand rule. Point the fingers of your right hand in the direction of the line of action, your R, and then bend your fingers in the direction of the force. Your thumb points in the direction of the positive torque. That's the direction of your torque vector. Positive torques cause counterclockwise rotation, and negative torques cause clockwise rotation, according to the standard sign convention. Now, where this starts to become really interesting, we've been doing all these parallels between translational and rotational motion, from velocity to angular velocity, from mass, inertial mass, to rotational inertia. Well, we have another one of those now for torque. Net force in the translational world corresponds to net torque in the rotational world. So Newton's second law, the translational version, net force equals mass times acceleration. In the rotational world, net torque equals moment of inertia times angular acceleration. And let me again just point out the parallels. Linear acceleration to angular acceleration, inertial mass to rotational inertia or moment of inertia, and force to torque. So that's going to allow us to solve and analyze a whole new set of problems and situations. Now let's go over equilibrium again, because we're going to start with some equilibrium problems. Static equilibrium implies that the net force and the net torque on an object are zero and the system is at rest. Dynamic equilibrium implies that the net force and net torque are zero. The system is moving at constant translational and rotational velocity. So it's moving, but no net force or net torque on it. So let's start off with a seesaw problem. A 10-kilogram tortoise, that's a big tortoise, sits on a seesaw 1 meter from the fulcrum. Where must a 2-kilogram hare sit in order to maintain static equilibrium? And what is the force on the fulcrum? Well, let's draw a diagram here of our seesaw first. And we'll put some fulcrum there. We know that our tortoise sits 1 meter from the fulcrum, so that distance there will be 1 meter. And over here at this end, we are going to have our tortoise. Let's see. That means that the force from the tortoise is going to be its force due to gravity, mg. 10 kilograms times g, we could just write this as 10g for the force. Now we've got a 2-kilogram hare. Where does it have to sit to maintain equilibrium? Well, we'll say that it's going to be somewhere over here. We don't know exactly where that's going to be yet, but its force is going to be 2g, and we'll call this distance x. And for the purposes of this problem, we'll ignore the mass of the fulcrum itself. It's massless. It's the perfect fulcrum, a magic fulcrum. All right. Well, in order to solve this, one of the things I'm going to look at first is understanding that it's in equilibrium. It's not rotating if they're balanced. Therefore, we can write that the net torque, which is equal to moment of inertia times alpha, must equal 0. Well, we can replace our torques with our net torque with the sum of our torques. So we have over here a 10G force at a distance 1 meter that's in the counterclockwise direction, so that would be a positive torque. So that's going to be, from our tortoise, the force 10G times its distance at which it acts, 1 meter, and it's perpendicular, so we don't have to worry about that angle component. And then we have, due to our hair, we have a clockwise torque, so that will be negative, so minus the force 2G times the distance from our center of rotation, x. And all of that has to equal 0. So then I have 10G minus 2GX equals 0, or 10G equals 2GX, x must equal 5 meters. And we have a follow-up question. What is the force on the fulcrum? Well, for that we can look at Newton's second law. In the translational world, net force equals mass times acceleration equals 0. And when we look at our forces, we have over here, if we call up positive, we have minus 10G from our tortoise. We have minus 2G from our hare. And we have some force up from our fulcrum. So plus the force of our fulcrum. And all that must equal 0. Therefore, the force of our fulcrum must equal 12G, which is going to be 12 times G, 10 meters per second squared, which is going to be 120 newtons. A fairly straightforward example, but we'll do some more here. Let's take a look at a beam. We have a beam of total mass m and length L with the moment of inertia about its center of ml squared over 12. The beam is attached to a frictionless hinge at an angle of 45 degrees and allowed to swing freely. Find the beam's angular acceleration. Well, the first thing I notice is it's giving us the moment of inertia about the center point, not about the hinge. So if you remembered the moment of inertia of a uniform rod about the end, you could use that. But let's just get some practice with the parallel axis theorem and say that the moment of inertia about the end is the moment of inertia about the center of mass plus mass times the shift squared, where this will be our distance d. So that's going to be, we have ml squared over 12 plus m, d is L over 2 squared. Put that together and I end up with 1/3 ml squared. So that's the moment of inertia in the current configuration we have for our beam here. Now let's define a couple things as we look at the problem. We said this is distance d. We have here the force of gravity on the center of our beam where it acts, which is mg. But if we're looking at torques, only the piece that's perpendicular to our line of action counts. So we're really after that component. That is going to be mg cos theta, because that's our angle theta right there, 45 degrees, which matches our angle theta over here. So we've got that figured out, mg cos theta, we know our distance d. We can go write our Newton's second law equation for rotational motion. Net torque equals moment of inertia times angular acceleration. And when I look at our net torques, we have, let's see, in the clockwise direction, so negative, we have minus mg cos theta, that force, times the distance at which it acts, L over 2, must be equal to I alpha. Which implies then that alpha must be equal to minus mg cos theta L over 2 times the moment of inertia, which is going to be minus mg cos theta L over 2. And we found our moment of inertia over here was 1/3 ml squared. So that's going to be 1/3 ml squared. And with just a little bit of simplification here, let's see, we've got an L, we've got an L squared. We've got an M and an M we can cancel out. So that gives us minus 3g cos theta over 2L. So there's our angular acceleration, using the parallel axis theorem to find the moment of inertia and Newton's second law for rotation. All right, we've done some Atwood problems with ideal pulleys. Now let's talk about real pulleys. We have a light string attached to a mass m wrapped around a pulley that has some mass mp and radius r. Find the acceleration of the mass. All right, to do this one, I'm going to start by drawing my pulley. There it is. It has some radius, capital R, and the forces acting on it and the places where they're acting. If that's our tension T, we have T acting that direction. We have the weight of the pulley, mass of the pulley times the acceleration due to gravity, and we must have some force of the pivot here, normal force, that's acting up. So there's our pulley diagram. All right, so starting there, let's take a look at Newton's second law. Net torque equals I alpha. But as I look at our torque is going to be, well, we have T at a distance r, and that's perpendicular, so our torque is going to be RT. I'm going to worry about magnitudes for now. And our moment of inertia for a disk is 1/2 mr squared, so our moment of inertia is going to be 1/2 mp r squared. So then our torque, RT, must equal 1/2 mp r squared, times alpha, of course, which implies then that our tension, T, divide r from both sides, is going to be equal to 1/2 mp r alpha. But we're looking for linear acceleration. We've got angular acceleration. Remember that alpha is equal to a over r, or a equals r alpha. We can replace r alpha with a to find that our tension is 1/2 mass of our pulley times a. All right, now let's draw a free body diagram for our mass over here. We have our object, we have tension up, and we have force of gravity down. In writing Newton's second law, we'll call down the positive y direction. mg minus t must equal ma. Or mg minus, we know our tension now, is 1/2 mpa must equal ma. Or mg equals 1/2 mpa plus ma. I can pull out an a there to find that acceleration is going to be equal to mg over m plus mp over 2. So we found the acceleration of the mass now that we have a real pulley that has some mass, some rotational inertia. Looking a little bit more detailed at torque, we have a system of 3 wheels fixed to each other that's free to rotate about an axis through its center here. Forces are exerted on the wheels as shown. What is the magnitude of the net torque on the wheels? Well, our net torque is just the sum of all our individual torques. So let's add those up. Starting with this one up here, we have a force of 2F acting at a distance of 2r, and it's perpendicular, so we have sine of 90 degrees, which is 1. And since this is causing a clockwise torque, let's make sure we call that negative. We also have a force over here of 2F at a distance 1.5r, still 90 degrees, but this one is in the counterclockwise direction, so that's positive. And we have a 3F force that's at, our 2F force, it looks like that's at 1r. Let me draw that a little bit more carefully, times 1r. And we have our 3F force, which is operating at a radius of 1.5r. also causing a counterclockwise rotation, so that's positive. So our net torque then is negative 4 FR plus 2 FR plus 3 times 1.5, 4.5 FR, or net torque equals 6.5 minus 4, 2.5 FR. Okay, let's do a ranking task. A constant force F is applied for 5 seconds at various points of the uniform density object below. Rank the magnitude of the torque exerted by the force on the object about an axis located at the center of mass, from smallest to largest. Well, we're going to have the greatest torque when we are the furthest away and the most perpendicular. So as I look at these different spots, it looks like we're going to have our maximum torque. Well, we'll start with the minimum when we're applying that force right toward the center, B. Then we'll go to C. Then we'll go to A because that's at an angle. And finally D because we've got that one that's perpendicular or most close to perpendicular compared to the axis of rotation here. So BCAD would give us the ranking of the torques from smallest to largest, assuming we're rotating about that point in the center. We could also look at ranking angular acceleration. A variety of masses are attached at different points to a uniform beam attached to a pivot. Rank the angular acceleration of the beam from largest to smallest. So if we want the largest angular acceleration, we want the most force the furthest away from the axis of rotation. So that's going to be at D, where we have 2m at the very end and then m right beside it. So D will be the most. Then it looks like C is the next most. We've got m at the very end and 2m just inside that. Then it looks like we're probably looking at A, where we have 2m at the very end. And finally, we have B, 3m at half the distance. So DCAB would give us the greatest angular acceleration from largest to smallest because we're looking at the ranking of the torques. Let's do a cafe sign example. A 3 kilogram cafe sign is hung from a 1 kilogram horizontal pole as shown. A wire is attached to prevent the sign from rotating. We're trying to find the tension in the wire. So let me just redraw that a little more simply over here. Use the ruler just to make things nice and neat. If there's our pole that goes with our sign, it looks like it's a 4-meter long pole, so 1, 2, 3, 4 meters. And as I look at the different forces acting on it, it looks like we have a force, well, it's 1 kilogram. So the force from the center of mass, its gravitational force, is going to be 1 kilogram times g, or 1g at the center. We have a 3 kilogram mass that's right over here, so that'll be 3g. And we have a tension from the wire over here. We'll draw that at the very end where it's acting. There's our tension, and that angle right there is 30 degrees. Now, since it's an equilibrium, we know the net torque must be 0, so we'll start there. Net torque equals 0, which implies then, as we add up the torques, that's going to be, we'll have T sine 30 times the distance over which it acts, over that 4 meters. That's counterclockwise, we'll call that positive. We also have minus 3g acting at 3 meters, negative because it's causing a clockwise torque. And we have minus 1g at 2 meters, negative because it's also causing a clockwise torque. Putting those together, sine 30 is 2, so that'll be 2t. So we have, 2t minus 9g minus 11g. So t is going to be equal to 11g over 4 sine 30, or 2, which is going to be 54 newtons. All right, let's finish up by looking at an old AP problem. Here we have the 2008 free response number 2 problem. You can find it here at the link on top. Go ahead and download that there. And let's take a look at that. This looks mighty familiar. We've got a horizontal rod with some length and mass. The left end of the rod is attached at a hinge, and we've got a spring scale attached to our wire in order to determine the tension in the wire. First thing we're asked to do is to diagram, draw and label vectors to show all the forces acting on the rod. All right, well, let's start by drawing our rod here. Something like that. And as I look, we're going to have the weight of the rod itself, mg. We're going to have the weight of our block on the end, we'll call that little mg. We have a tension here at some angle 30 degrees. And we also have a force from the hinge, which in order to balance all this out must be going somewhere up and to the right. So that's the force of our hinge. Okay, capital M we'll call 2 kilograms. Little m is 0.5 kilograms, and the whole thing has a length of 0.6 meters. So there's A. Looking at part B, calculate the reading on the spring scale. Well, the net torque has to be equal to 0, which implies that, well, let's add up all our torques. We've got TL sine 30. We're going to assume it pivots around here. So that length is L, minus, we'll have little mg L, negative because it's causing a clockwise torque, minus capital mg L over 2, the mass of our bar causing a torque, its force. All that has to equal 0. Therefore, our tension must equal, we'll have G capital L over M times M plus capital M over 2, divided by L sine 30 degrees, which implies then that our tension must be, well, sine 30 is 1/2, so that'll be 2G, L over L cancel out, times M plus capital M over 2, which is going to be 2 times 10 meters per second squared, times our little mass, 0.5, plus our M over 2, 2 kilograms over 2 is 1 kilogram. So 20 times 1.5 is going to be 30 newtons. So there's part B. Moving on to part C. The rotational inertia of a rod about its center is 1/12 ml squared, where m is the mass of the rod and L is its length. Find the rotational inertia of the rod block system about the hinge. All right, well, for C, the moment of inertia of our system is going to be the moment of inertia of the rod plus the moment of inertia of the block. So we can find the moment of the inertia of the rod about its center of mass is 1/12 ml squared. If we want that about the hinge, we can use the parallel axis theorem. Just in case you didn't remember what the moment of inertia of a rod is about its end. So the moment of inertia of the rod about the hinge is going to be the moment of the inertia of the rod about its center of mass plus md squared, because we've got parallel axes and our initial one is about the center of mass. So that's going to be 1/12 ml squared plus m times L over 2 squared, which is ml squared over 12 plus ml squared over 4. Where the moment of inertia of the rod about the hinge is just ml squared over 3. And we know the moment of inertia of the block is ml squared, little ml squared. So when we put that all together, the moment of inertia of the system is 1/3 ml squared plus little ml squared, which is going to be L squared times capital M over 3 plus little m, which is going to be 0.6 squared times, we have 2 kilograms over 3 plus 1/2 kilogram, which comes out to be about 0.42 kilogram meters squared. All right, one more part to the problem, part D. If the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system. All right, well, net torque equals moment of inertia times angular acceleration. Therefore, our angular acceleration is the net torque over the moment of inertia, which is mgl plus big MG L over 2, all divided by the moment of inertia. We no longer are worried about that tension in the wire because we cut it, which is going to be equal to, well, we can factor out a GL over I, M plus big M over 2, which is going to be 10 meters per second squared times our length 0.6 over our moment of inertia 0.42 kilogram meters squared times 0.5 kilograms plus 2 over 2 is going to be 1 for a total angular acceleration of 21.4 radians per second squared. All right, hopefully that gets you a good feel for torque and Newton's second law for things that are rotating. We'll get more into that in our next lesson on rotational dynamics. Thanks for watching Educator.com. We'll see you again soon. Make it a great day, everyone.